definitions of observational data and how it is related to QPO model testing. QPO stands for quasi-periodic oscillations, and I kind of assume here that you are already familiar with what quasi-periodic oscillations are. And there's probably not enough time to dig deeper into that rabbit hole anyway. So, but what I'm not sure is if you're familiar with how the raw X-ray data look like, and not just the fancy plots you can see in the articles about quasi-periodic oscillations. So, first, where we get the data from. Most of the X-ray data that we analyze in order to analyze quasi-periodic oscillations come from RXT observatory, which is probably the best source of those data. Notice especially this parameter, effective area. It's probably the most important parameter of the detectors. So here we have a light curve of one of QPO of the sources which exhibits quasi-periodic oscillations. As you can see, it's not very much interesting. So when we do the Fourier transform and move to the frequency domain, we obtain something like this. This is a power density spectra. It tells us how much power there is at each frequency. And as you can see, there are no QPOs yet. This is a power density spectra obtained from 2 seconds of the light curve. So next thing we can do to get rid of the noise is to average several of such power density spectra. We obtain something like this. This is a power density spectra which in total has integration time of 64 seconds. And it's obtained by averaging 32 2 seconds power density spectra. And here you can see that there probably is something here at about slightly below 800 Hertz. We can make sure by fitting the power density spectra, but it's correct, there is quasi-periodic oscillation at about 800 Hertz. If we are a little bit more clever with the data analysis, we can make much more of those power density spectra and plot them into so-called spectrogram. Each column here consists of separate power density spectra. There are about 300 of them, and here we can track the quasi-periodic oscillation, at least the one of them. This source is known to have so-called twin peak quasi-periodic oscillations. When we do so-called shift and dead method, which means that we move all the individual power spectra so that the quasi-periodic oscillation is on a single line, then we do the average of all the spectra, we would find out that there is an additional quasi-periodic oscillation at about 1000 Hertz. But it wouldn't be visible here anyway, so I'm not going to do this. But if we if we have some model to explain the quasi-periodic oscillations, we first should make sure that given the detectors we have, that we are at least in principle able to to detect some features specific for the model. So how do we do that? And in case the present detector is not capable of doing that, how can we know that the future detector will be capable of doing that? We can use so-called response matrix for that. In computer it's a file. It's just a matrix which tells us, or we obtain this matrix in a way that we take the detector and we put on that detector some very well-known signal, and we look at how the detector behaves, what kind of data we obtain from the detector for this very well-known signal. So next time we have some known signal, then when we convolve it with this response matrix, we get the data which we work with. Actually, when we do the model fitting, we usually fit the data. But what we actually want to do is to fit the underlying physical flux. And since with working with quasi-particle stations, we are really on the edge of the capabilities of detectors. There is a huge difference between the real physical flux and the data that we see. So now a response matrix gives us a response of the detector to a static signal. But when we study QPOs, we are interested in studying time-dependent signal, varying on a very short time scales. So the easiest way how to proceed is to simulate a light curve, then cut this light curve onto small pieces of stationary flux, and each of these small light curve convolve with the response matrix. Then we put it all back together, do the Fourier transform, and then we know how the detector observes our signal. So we have done some simulations on this. First, for the model of a hotspot orbiting at this radius, and with relative eccentricity of 10%, when we compare the current RXTE detector with proposed loft detector, we can see that when RXTE is able to see just the main signal and only for the highest normalization of the signal, loft detector is capable of seeing not just the main signal but also higher harmonics and the radial epicyclic frequency coming from the eccentricity of the orbit, and this all the way up to the lowest normalization. We have also tried another models And I see that LaTeX has probably done some nasty stuff here. This is a fit, and there should be data everywhere, but I don't see what's going on. Okay, so there are two different models, one with multiple spots at two different radii, and one of drifting optically thin torus. And here again, you can see that where RxT is incapable of observing any signal, Loft is perfectly capable of seeing not just the signal, but also the higher harmonics and other stuff. Okay, so some conclusion to this is whenever we want to fit a model to some data, and those data are kind of on the edge of our capabilities of detectors, we should consider using the response matrix to do the proper fitting. Also, this approach tells us that whether the new detector helps us to distinguish different models from the data, and following this, the data analysis procedures can be optimized for the task long before the detector is actively collecting the data. And this is all. Thank you for your attention.